Let's look at 18i. This is the lesson, particularly for HR students. We need to look at what the derivatives of inverse trig functions are in this lesson. So let's review the inverse trig functions. I want to give you 5 minutes so you can pause the video, try to go over each basic trig function, like y cosine x, y cosine x, y cos tangent x. If you wanna also go over y equals cosecant x, y equals secant x, y equals cotangent x, feel free to do so. But of course, for the inverse trig functions, we only focus on the inverse of these 3 primary trig ratios. So this reason, in this table, we only include 3 primary trig functions. I hope that you got enough time to go over those 3 primary trig functions and their inverse functions. So for y equals sine x, its natural domain should be all real numbers. However, if we want to define its inverse sine function, so we need to restrict the domain to form a 1-to-1 function on this particular domain. So I hope that you guys remember we take negative pi over 2 to pi over 2 closed interval as the restricted domain when we define the sine inverse function. So based on this domain, we can keep the range -1 to 1 closed interval the same. Based on this domain, we defined y equals x sine x or sine inverse x. So you know, if this function is the inverse of this one, we just swap x and y. Therefore, we also swap the domain and the range. So the domain of the inverse function should be from -1 to 1. The range should be from negative pi over 2 to pi over 2 inclusive. This is the graph for the inverse. I did not graph the original function. Likewise, the natural domain for cosine function should be all real numbers as well. In order to define the inverse cosine function, we restrict the domain to 0 to pi inclusive. Based on this domain, we still can keep the range the same. Based on this domain, we defined the inverse cosine function as arc cosine x or cosine inverse x. We swap the domain and range. Therefore, the domain of the inverse cosine function should be from -1 to 1 inclusive. The range is from 0 to pi inclusive. So this is the graph for y equals arc cosine x. You can graph y equals cosine x yourself. Y equals tangent x, since it's sine over cosine, cosine x cannot be 0. Therefore, we do have the restrictions in the domain. So x cannot be k pi plus pi over 2. K is an integer. When x equals k pi plus pi over 2, those vertical lines are the vertical asymptotes for tangent function. So in order to define its inverse tangent function, we restrict the domain to negative pi over 2, pi over 2, open interval. Based on this domain, we still can keep the range the same. Y can be all real numbers. Based on this domain, arctangent function can be defined. So y equals arctangent x or tangent inverse x. This is the inverse of tangent x. So we swap the domain and range. X can be all real numbers, but the range should be from negative pi over 2 to pi over 2, open interval. So this is the graph. Vertical asymptotes become horizontal asymptotes. So y equals pi over 2, y equals negative pi over 2 are the horizontal asymptotes for the inverse tangent function. And I also hope that you know all those things. So sine inverse x is not 1 over sine x or cosecant x. Sine inverse is just inverse. We also introduced when can you change the negative exponent to 1 over sine. So this one should be sine x to the power of -1. So you put a -1 outside sine x entirely. This is 1 over sine x. If we put a -1 between sine and x, this one means inverse. So sine inverse x is the inverse function of y equals sine x. Cosecant is the reciprocal function of sine x. Okay, the same principle can be applied to arccosine and arctangent x. Right now, we need to find the derivative of the inverse trig functions using implicit differentiation in section 2. Let's find the derivative of y equals arc sine x. So if I want to find its differentiation, I need to change this one back to x equals sine y. Based on x equals sine y, I can apply the implicit differentiation. Differentiate x is 1. Differentiate sine y should be cosine y times y prime dy over dx. So dy over dx equals 1 over cosine y. Then how can I use sine y, this x, to represent cosine y? Since we know sine square y plus cosine square y equals 1. Cosine square y equals 1 minus sine square y. So cosine square y equals 1 minus x squared cosine y. Mathematically, cosine y can be positive negative square root of 1 minus x squared. However, based on the definition for the arcsine function, we know arcsine x, this y, only can be between negative pi over 2 to pi over 2. The fourth quadrant to the first quadrant. So this angle y is in the fourth quadrant. Cosine value should be positive. In the first quadrant, cosine value is still positive. Anyways, cosine y only can be positive square root of 1 minus x squared. Therefore, dy over dx, which is the differentiation of arcsine x, equals 1 over square root of 1 minus x squared. Of course, x should be between negative 1 and 1 inclusive, which is consistent with the domain of the arcsine x. Like the first one we did, we can derive the differentiation of arccosine x using the same idea. So y equals arccosine x. Let's change this form back to x equals cosine y, using the implicit differentiation to differentiate this one. So 1 equals negative sine y times dy over dx. Therefore, dy over dx equals negative 1 over sine y. Sine square plus cosine square y equals 1. Sine square y equals 1 minus cosine square y. Sine square y equals 1 minus x squared. Sine y should be positive negative, but is that possible for you to have both of the results? So you need to look at, for x can be between negative 1 and 1, this y has to be between 0 and pi inclusive. The angle y is between 0 and pi inclusive for sine, from the first quadrant to the second quadrant. Anyway, sine is always positive. Therefore, sine y only can be positive square root of 1 minus x squared. So dy over dx is negative 1 over square root of 1 minus x squared. So this is the differentiation of arccosine x. I hope you can try to find the derivative function for y equals arctangent x, y equals arccosecant x, y equals arcsecant x, and y equals arccotangent x yourself first. C is included in our core textbook. However, D, E, F, they are not even included in the formula booklet. We still try to derive each derivative just because we want to extend our knowledge further. But don't worry about DF. Even if you have trouble in finding the derivative functions in DEF, they are not required for HR students either. So we just try to extend the knowledge, that's it. So after you got a chance to derive each derivative function in CDF yourself. Let's check your answer with my answer. So C is a regular one. You have to know this one. So we do the same thing, right? X equals tangent y, then dy over dx can be obtained through the implicit differentiation. So dy over dx equals 1 over secant square y. Then secant square y with tangent y, they should have this relationship. So secant square y equals 1 plus x squared. Therefore, dy over dx, which is the differentiation of arctangent x, is 1 over 1 plus x squared. D. The same. X equals cosecant y. Then we apply the implicit differentiation to find dy over dx is negative 1 over cosecant y times cotangent y. So for this cosecant y, it's just x. So I sub x in for cosecant y. Then we only need to look for cotangent y in terms of x. So that's how I can find cotangent y in terms of x. So the differentiation of cosecant x should be negative 1 over x square root of x squared minus 1. E. Like D, it's not required in that core for HL students. So we just change the form to this form and implicit differentiate it. So dy over dx equals 1 over secant y tangent y. So secant y is x. Let's just sub in. Then tangent y and the secant y, they should have this relationship. So tangent y equals square root of x squared minus 1. Therefore, dy over dx equals 1 over x square root of x squared minus 1. Arc cotangent x. So x equals cotangent y. Then use the implicit differentiation. We can get 1 equals negative cosecant square y times dy over dx. dy over dx equals negative 1 over cosecant square y. So the relationship between cosecant y and the cotangent y should have this one. This is the identity we learned in the trig identities. So 1 plus x squared equals cosecant square y. So 1 plus x squared to replace cosecant square y. So the differentiation of cotangent x is negative 1 over 1 plus x squared. Here are the homework questions. Try to apply the differentiation rules of y equals arc sine x, y equals arc cosine x, y equals arc tangent x to find the derivative of more complicated looking functions involving arc sine, arc cosine, arc tangent in your homework questions. This is the end of this lesson.